Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy them. So check out Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And don't forget to go to dataengineeringpodcast.com/chat to join the community and keep the conversation going. Your host is Tobias Macy, and today I'm interviewing Usman Masood and Derek Nelson about PipelineDB, an open source continuous query engine for PostgreSQL. So, Usman, could you start by introducing yourself?
Yeah, I'm Usman. I work as an engineer at Stripe. Previously, I was involved with PipelineDB as the chief architect and worked for a couple of years on the project.
And Derek, how about yourself?
So I'm the founder and CEO of PipelineDB.
And going back to you, Usman, do you remember how you first got involved in the area of data management?
I think for me, it was kind of just randomly stumbled into it. In school, I focused a lot on System Z stuff and then built a few data processing pipelines at my first job. And then when I was looking for a new job, saw PipelineDB as a potential opportunity. I'd always wanted to work on an open source project or like something where I could kind of give back to the community. Seemed like a cool project. So talked to Derek and, things kind of went from there.
And Derek, how did you first get involved in the area of data management?
So it all started at the last company I worked at before I started this company. It was an advertising technology company called AdRoll. I started there when it was a very small company and ended up growing really big. And I was on the engineering team, and I took over the responsibility for basically all of their data management infrastructure. And as the company grew and the scale grew explosively, we had to build a lot of things that didn't exist yet, a lot of new interesting technology to handle just the huge scale involved in running an advertising company. And after doing that for a few years, I had learned a lot about products that I wish had existed because we had to build them ourselves at AdRoll. And when I was ready to move on and do the next thing, I started PipelineDB based on my experience at AdRoll.
And so can you give an overview of what PipelineDB is and some of the motivation and story behind creating it?
Yeah, sure. So it really begins with the experience I had at AdRoll. As I mentioned, we were processing huge amounts of data. By the time I left, we were reaching more than half the internet per day with ads, and we were analyzing all of that data in real time, which is a pretty hard problem to solve at that scale. But the key observation was that most of what we wanted to know about this data we were processing, most of the computations required to learn those things were fairly straightforward. We were counting a lot of things, running aggregation queries and things like that. And we built a lot of complex application code, custom application code that we used to achieve those things. And there was really no off-the-shelf product that allowed you to say, okay, take this huge, massive, continuous stream of data and just run these simple aggregations on it as efficiently as possible. And that's essentially the problem that PipelineDB solves. Instead of requiring people to build their own custom application infrastructure or use some of the more complex stream processing infrastructure out there, it allows them to declare the aggregation queries they want to run on these massive flows of data, and it then runs those calculations continuously in real time as data flows into the system. But the key innovation is that PipelineDB only stores the output of these aggregation queries. So another key observation we had at AdRoll was that the input data set was much, much, much larger by multiple orders of magnitude than the output because we were doing aggregations. It starts out with this huge voluminous stream of messy log data, one event per ad served or one event per click served or whatever. And by the time it gets processed, it's much, much smaller than that. It's just aggregated down into a relatively small number of rows, bucketed by hour or day or customer or user. And so when we looked at that huge differential between the size of the input and the size of the output, we saw an opportunity to build a system that just never had to store the raw granular data. And because the bottlenecks in most database technologies is generally the disk, that allowed us to avoid an enormous amount of disk I/O by just aggregating all of this data in memory, only writing out the compact output to disk. And that makes PipelineDB extremely efficient, even running it on a single server deployment.
And later on, I definitely want to get into some of the scaling aspects in terms of the system architecture that would be most beneficial for this deployment, and some of the discussion around discarding the raw data and some of the options there. But first, I'd like to cover what types of use cases this enables that would otherwise be impractical or intractable, and some of the main types of industries that would benefit most from the pipeline technology.
So the primary area of use cases is anywhere there's like a real-time analytics dashboard being used at a company. PipelineDB is going to be a really good fit for powering that, because the main drawback of using this technology, or trade-off rather, is that you have to know these queries in advance. You have to declare them in advance, and then as the data runs through them, the results are incrementally computed. So anywhere where you know the queries that you want to run on these large streams of data in advance, PipelineDB is going to be a really good fit. And in our experience, we've seen that mostly in the area where there's reporting dashboards, real-time analytics dashboards, things like that. People are using PipelineDB to power those things on basically really small amounts of hardware, and on also with large amounts of input data, which before PipelineDB was around, it was a much harder problem to solve for the reasons that I mentioned before, is that you had to build larger scale, usually custom application infrastructure to do these aggregations in real time. PipelineDB just makes it really, really simple. So in terms of the things it enables companies to do that they wouldn't otherwise be able to do, it allows them to analyze more data faster, essentially. They're able to, in many cases, analyze data sets that they wouldn't be able to analyze at all before, or in real time. So software companies with deep technical expertise, they can build this infrastructure, and they do themselves. So PipelineDB makes a lot of sense for companies that are producing a lot of data, but they're not necessarily software companies. They don't necessarily have the experience or the staff to build complex stream processing infrastructure. So it makes it much easier for them. And in terms of industries where we see PipelineDB being used heavily, it's a pretty broad cross section, honestly, because you can think of pretty much any company in the world nowadays. Companies are more and more becoming data-driven companies, and so pretty much every company out there will have some sort of software infrastructure that's ultimately powering real-time analytics dashboards that other people in the company are using. So the set of companies using PipelineDB is extremely broad. We do see increased usage in a few different verticals. Ad tech is one of them, which isn't surprising, because this was essentially conceived out of experience from ad tech. Telecom is another vertical where we see a lot of usage. And then beyond those two, it's a pretty broad cross section.
And what are some of the major architectural concepts and design components that users of PipelineDB should be familiar with to be able to use it effectively?
I think the first, and Usman, you can add to this if I miss anything. The first thing is to have a proficiency in SQL, I think, at a high level, because everything that you do with PipelineDB, you essentially do with SQL. So you'd want to have some proficiency with SQL, know how that works. You would also want to have a good understanding of how PipelineDB scales across cores on a server. We built it to be highly parallel, because stream processing is very CPU intensive because you're running all these computations on huge flows of data coming in. So you'd want to have an understanding of how all the work required to run these continuous queries scales out over the CPUs on the system that you're running PipelineDB on, so that you can properly take advantage of all the hardware capacity available, I would say. Is there anything else I missed, Usman?
Yeah, I think that covers most of it. I think the kind of high level concept here is I think, which Derek has mentioned before as well, is understanding if your data can be efficiently summarized, and sometimes in that you might lose some level of accuracy. Like, for example, if I'm trying to count the number of distinct elements in a stream, if I'm trying to do it 100% accurate, I kind of have to store on the order of unique elements. I have to store that information somewhere. But if I'm happy with a little bit of an error, if I don't think that's that big of a deal, then you can use some kind of probabilistic summary structures underneath the hood to approximate those answers. So PipelineDB internally will leverage a bunch of these probabilistic data structures automatically for you, so you don't even have to think about what's happening. But you still need to have the understanding that when you do summarize data and you're trying to do it efficiently, you might lose some level of accuracy. For the most part, what I've seen is that when you are dealing with such large volumes of data and you're trying to get aggregate information out of it, you don't really care if you saw 1 million elements or 1,000,002. That level of accuracy is not that important. You're not taking extremely hardcore business decisions. You're mostly just getting charts and trying to see directionally how things look.
Yeah, that's a really good point on this question. As Usman said, a lot of the infrastructure that allows us to even run these continuous aggregations on essentially infinite streams of data use probabilistic data structures. Like for example, an extremely common aggregate operation that users use PipelineDB for is counting distinct, which means counting the number of distinct input elements. So this might have a use case in website analytics if you want to know for each hour how many distinct users viewed this URL, and that uses count distinct in PipelineDB. But to do that with perfect accuracy, as Usman said, you have to store all of the unique elements you've seen, and then when you get a new element coming in, you say, have I already added this? If not, then increase the distincts count. If so, don't do anything because it's not unique. And we use hyperlog for count distinct, which is a very compact data structure that allows you to estimate the cardinality of the input set with a very small memory footprint. And the trade-off is that it has a small margin of error. So most of the error margins with these probabilistic data structures in PipelineDB, have a error margin of usually less than 1%. Like hyperlog is, I think by default, 99.2% accurate. And as Usman said, when you're dealing with huge numbers, you don't really care if it's 1 million or 1,000,002. So that's the kind of error margin that users are generally okay with accepting in PipelineDB.
And so, given the fact that PipelineDB is implemented as a plugin for PostgreSQL, and there are a number of other very interesting and useful plugins within that ecosystem, particularly things like some recent entries, Timescale and Citus, I'm wondering what level of compatibility exists between PipelineDB and some of those other useful plugins.
So with the two that you mentioned, we get asked about those pretty often. And currently there's no native integration with any other extension. So any kind of interoperability you would have between PipelineDB and another extension would be done through the primitives exposed by Postgres. Since they're all Postgres extensions, you could integrate them using whatever interfaces Postgres provides you, which are things like triggers, logical decoding, streams, replication, things like that. It's possible to integrate these extensions with those standard primitives. And in the future, I think we'll almost certainly have a native integration with TimescaleDB, just because the use cases for TimescaleDB and for PipelineDB have a lot of overlap. They're both essentially time series processing engines. Timescale DB is a bit different in ours, is that it stores granular data and allows you to query it very efficiently, whereas we don't store granular data. But the use cases are very similar. So we basically solve a lot of the same problems with two fundamentally different approaches. So it makes a lot of sense for these two integrations to be integrated in the future. So I think we'll almost certainly have something in that area within the coming months. In terms of Citus, there's not as much overlap in use cases as there is between us and Timescale DB. So we don't have anything to work in the works in terms of integration with them, but it is something that we get asked about relatively frequently.
Yeah, as I was looking through the documentation for PipelineDB, I was envisioning using timescale for storing the high granularity data after it's been pre-aggregated by PipelineDB, so that you can sort of have the best of both worlds, where you have a constant view of what the current value is, but you still have the ability to go back and do ad hoc analyses after the fact, rather than discarding the data or having to pipe it twice into the same database or use them in separate databases.
Right. Yeah. Fundamentally, that's pretty much what everybody wants to do with the two systems together, as far as I understand it. And in a lot of cases, I think that would work really well. For a lot of our users, storing the granular data, it's not even an option. It's not that they don't want to do it. It's that they can't, because they're dealing with too much data. And so a lot of our biggest users, they'll keep it somewhere. I mean, you're not going to throw away the granular data, but they'll store it somewhere cheap, like S3, for example. And then when they want to run ad hoc queries on it, they'll use something like Hive or Redshift to do batch queries, because those don't have to have real-time latency. Generally speaking, if you don't know the query you want to run in advance, then it probably doesn't have a real-time requirement anyways. So our biggest users do things that way. But for a lot of use cases, storing all the granular data probably would be feasible. And I think in those cases, it would be really useful to have both of these extensions work together.
And in terms of the ingestion capabilities for PipelineDB, I'm curious what some of the common patterns are for being able to create and populate the data streams that Pipeline is processing.
Yeah, so in terms of creating the streams, it's a super simple SQL query. Basically, you just a stream is essentially the same as a table. So you just create a table with some columns, and then the stream exists. In terms of getting data into the system, that's also pretty simple. You just use regular SQL insert statements or copy. The bigger deployments are almost always using some sort of message bus like Kafka or AWS Kinesis, and we have connectors for both of those messaging buses that connect directly to PipelineDB. So, for example, with the Kafka connector, you basically point it to your Kafka cluster and map a Kafka topic to a PipelineDB stream, and then you just tell it to go, and it will just start consuming data into PipelineDB from Kafka. Another, I think, important observation in terms of how people are ingesting data into PipelineDB, I would say, is a lot of them, because Postgres has such rich support and functionality for JSON, a lot of users are actually creating these streams with only one column, and it's just a JSON type. And then so each stream event is just like a JSON dictionary, for example, that gets written to that stream, and then all of their continuous queries unpack that schemaless event using Postgres's rich and mature JSON support for things like pulling out object keys and unpacking arrays and things like that. So in general, that's how most people are getting data into the system.
And so I think the in-memory stream table is definitely a very interesting abstraction. And I'm wondering if you can dig a bit deeper into how Pipeline overall is architected and implemented, and some of the evolution of the system since you first began working on it.
Yeah, definitely. And I'm sure Usman could add to whatever I have here, because he was a big part of how this part of the system developed. Let's see, in the beginning, we had what's called I think we called it a stream buffer, which was it was a shared memory it was a shared memory chunk of memory space. And shared memory is just a region of memory on a system that multiple separate processes can interact with. So as new data would come into the system, the process writing that event to the system would write to this stream buffer, and then other processes would essentially read from it. And as all of the events were read from the stream buffer, they would get marked as read by all the continuous queries that need to read them, and then that space would be reclaimed by new incoming events. So it was more of it was like a circular sort of queue that would just constantly get filled up and emptied as new data came into the system, and as continuous queries read those events. So that was like the very, very early implementation of the in-memory representation of streams. And then it got much, much better. And I think, Usman, you might want to explain this. You probably do a better job than me. We moved to using an external dependency. We went for as long as possible without depending on any external libraries with our code, so that it was as easy to install as possible. You wouldn't have to install anything else. And this is such a critical part of how the system works that we decided to go with an external messaging library called ZeroMQ.
Yeah, we actually played around with this other library called NanoMessage before. Remember that? Yeah, so as Derek was saying, this in-memory stream buffer abstraction was kind of pretty important early on, but as we added kind of more parallelism or more concurrency to the system, we started realizing there was actually pretty difficult to maintain like a high-performing and bug-free implementation of this in-memory stream buffer. And so then, like, okay, maybe you should investigate other messaging libraries, because essentially, like, at the heart of it, if you think about it, it's like a messaging. You need some sort of messaging abstraction. You have incoming data coming in from potentially multiple processes, because depending on how many insert threads or how many insert processes you have, that's kind of the number of concurrent writers you have. And then within PipelineDB, we have two kind of layers of processes called workers and combiners, where workers do some initial work on the incoming streaming data, and then they pass the output to another set of processes called combiners, and those combiners do some more processing and then eventually persist it to disk. And there's crosstalk between all these processes. So any insert process could potentially write to any worker, and then any worker can potentially write to any combiner. So there's a lot of crosstalk happening. And so eventually we start off with a stream buffer, then we made like a sharded stream buffer, and kind of like eventually just gave up on the idea and started using NanoMessage, which is a messaging library made by the same guy who made ZeroMQ, I believe, and stuck with that for a while, but eventually gave that up for ZeroMQ when we started working on PipelineDB Enterprise, because ZeroMQ, I forget exactly why, but it was better for the nice thing that it gave us was that you could talk to a local process or a remote process with the same abstraction. And so we could like potentially talk to a combiner on a different node completely from a worker process, as if we were talking to a combiner on the local machine. So it kind of gave us this idea of like, even if you have 10 nodes with PipelineDB running on it, you would kind of think of it as a single giant node with all those processes, all those combiner processes running on.
And what are the capacities and options for being able to scale a pipeline system, both in terms of vertically by adding more system capacity and horizontally by adding new instances to the cluster?
Yeah, so the open source PipelineDB core is and always has been designed to run on a single server. And that doesn't necessarily mean that the open source core is like a toy or like a trial version or anything like that. It's absolutely not. And the reason is because we have this system that allows you to perform all of this computation without ever storing any raw data at all. So that allows you to achieve a level of performance and scalability on a single server that you would never even be able to come close to relative to a system that has to store all of the granular data. So the open source core runs on a single server. You can add multiple read slaves for scaling out reads by using Postgres replication, for example. So you can have multiple nodes, all the data is coming into one node, and then all the changes being made as a result of that data is replicated out to all these other slaves, and you can fan your read workload out to all of those. In terms of scaling writes, that's where our business model comes in. we have a commercial extension to the open source PipelineDB core that adds horizontal scaling support to the system. So you can create PipelineDB clusters with this extension that shards the write workload and the read workload actually out to multiple nodes, and the whole thing still just behaves as one large logical PipelineDB deployment. So there's nothing new about the protocol or the interface or anything like that. It's still just an endpoint that your client connects to, except the workload and the read and write requests that are happening get sharded out to multiple nodes, which makes the system much more scalable. And that's how we make money primarily. We sell licenses to the clustering engine to companies that really need like just a huge level of scale that they haven't been able to achieve with one instance. And the commercial extension also adds high availability support, failover. So it has like things like replication. You can lose multiple nodes and the cluster will continue operation without any loss of service interruption. So that would be the primary way that people could scale.
And even when it comes to vertical scaling, PipelineDB actually can tremendously scale vertically because of just the system architecture. A lot of the parallelism happens in a manner where typically when you're trying to scale up any system, if there's a lot of contention of the data that they're trying to write to at the same time, that's kind of the main bottleneck. Otherwise, the number of CPU cores can work independently and kind of perform at the max speed at which it's possible. The way PipelineDB is architected, as I previously mentioned, there's two groups of processes that are important. One is called the workers and one is called combiners. And the workers don't share anything between each other, so they can literally go as fast as possible. And combiners are the ones which may be bottlenecked on writes, but the combiners also, the way it's architected is that two combiners will never write to the same row. And so that ensures that we don't have a lot of write contention either. So if you just get like a node which is 64 cores or something, PipelineDB will be very efficient at making sure that it utilizes those 64 cores very efficiently, whereas a lot of systems traditionally may or may not be able to do that.
Yeah, that's a really good point.
Given that the inbound data is not persisted to disk until after it's gone through the workers and combiners, I'm wondering what capacity there is for guarding against data loss in the event of a power failure or system reboot or something like that, where you don't necessarily have the advantage of the write-ahead log to be able to repopulate that stream, and some of the strategies for being able to mitigate that loss.
Yeah, that's a really good question. So all of the interaction with disks by the combiner processes is still fully transactional. So if a combiner has updated the row that it needs to, or the rows that it needs to, and that succeeds, the result is durable. So it will survive a power failure just like any other row in a regular Postgres table. The area for potential data loss is the short period of time where a set of rows written to a stream are currently being processed by the worker. They're basically in between the worker and the combiner's final stage of writing to disk. And that the size of the number of events that can be in that batch is a tunable size. And that's basically the largest amount of data that you could potentially lose, because if there's a power failure between the time a batch of events is being processed by the worker and by the time it's been persisted to disk, those events will be lost. But you can tune the size of that batch depending on your requirements and how much data you're potentially willing to lose. And then after that point, writes will just fail because the system would be down. So clients would never be able to write to the system at that point and think that they succeeded. They would be notified that they failed. So basically one batch is the amount of data that you can potentially lose.
And so is the information in the stream tables maintained with a write-ahead log, or is that purely in memory and that would be lost as well?
So yeah, all writes to the streams are not persisted to a write-ahead log anywhere. They're just never written to disk. The only thing that's persisted to the write-ahead log are the changes being made to the on-disk aggregate output maintained by the combiners. But yeah, stream events by design are never written to a write-ahead log.
Yeah, PipelineDB, however, does offer like a few different modes of inserting into streams, and Derek can probably speak more about it because I'm sure there's like more work that has happened on this. But when you insert into a stream, there's similar to like how there's consistency kind of levels in databases. There's also like kind of ACK levels that we have in PipelineDB where you can insert into a stream and you can be like, okay, just insert and forget about it, or insert and wait till a worker reads it, or insert and wait till a combiner actually has processed it and sync and like written it to disk. And so there's like a few like tuning parameters there where depending on how much data loss you're comfortable with, you can tune that kind of consistency level up or down. Obviously, the more you push it up, the lower your performance will get. That's just kind of an artifact of how the system works. But there is like tuning parameters in place for users to be able to kind of determine ahead of time, hey, this is the data loss that I'm fine with versus not.
Yeah, that's a good point. So there are configuration parameters you can use to ensure that all writes to all streams are fully transactional. They either fail or succeed completely, but there'll never be any silent data loss. All of our users, as far as I know, actually, they elect not to use that level of stream insertion consistency because it just lowers performance, and they don't, users generally don't mind losing a small batch of events, and this is a pretty rare occurrence anyways. We have huge users that have been running PipelineDB for months and years with no crashes or failures or anything. So the idea of losing a batch of events due to a power failure or crash is actually pretty rare. So our users generally are fine with taking that very, very, very tiny level of risk with just one small batch of events. And also because they're writing so many events to PipelineDB that losing one batch it's not even a big deal. It's like a rounding error. A lot of users are writing tens, hundreds, some even millions of events per second, and by default one micro batch is 10,000 events, so it's relatively negligible.
And for the input stream table spaces, is it possible for any other processes to read from those, or is that purely the domain of the workers? And also, is it possible to use another table that's already existing on disk as an input to a stream?
So I'll answer the second part of your question first. To use a regular table as a stream, this kind of goes back to the previous discussion about integration between extensions. You would use the primitives given to you by Postgres. So you could have a logical decoding process, for example, that listens to all of the changes being made to that table and then writes that result out to a stream, which is actually pretty easy and works fairly well. In terms in the first part of your question, in terms of what else can read from streams, so the main abstraction we've talked about so far, these kind of continuous aggregations, that's done by what we call a continuous view. And a continuous view basically always aggregates data and then outputs the result to disk. The other fundamental abstraction that PipelineDB provides is called a continuous transform. And a transform is different than a continuous view in that it doesn't persist anything to disk. All it does is it reads from a stream, applies whatever query you've used to define it to each event in the stream, and then outputs that transformation to another stream. So you can also read from streams with those, and then you can chain all of these things together into arbitrary topologies of continuous computation. You could think of this topology as like a directed acyclic graph of continuous SQL queries, because continuous views actually output the incremental changes being made to the tables that back them. Those changes are actually output to another stream. So you could have arbitrary combinations of continuous views and transforms all outputting stuff to different streams, connecting together and performing pretty complex operations. And people have done some really interesting things and come up with different ways to combine these abstractions in pretty clever ways, which is pretty interesting. But the important thing is that these abstractions provide enough flexibility to do pretty much anything you want. So,
and Also, just to clarify, I believe that you alluded to the fact earlier that it's possible to have multiple continuous queries running against a single stream so that you can have different aggregates computed on the same source data.
Yes, absolutely. So that's the norm in terms of how people use the system. There typically will be a small number of streams and a large number of continuous views and transforms. Each event written to a stream has a small bitmap associated with it, and each slot in the bitmap corresponds to each of the continuous queries that need to read it. And as soon as each continuous query has read this event, they flip the bit, and once all those bits are set to 0, then the event is discarded. But yeah, absolutely, the norm is to have a small number of streams fanning out to a large number of continuous queries.
And since the data being processed by the continuous queries is potentially unbounded as the new data continues to stream through, I'm curious what your approach is as far as checkpointing or windowing the data to determine when it should be persisted to disk.
Yeah, so this is determined by a couple of different tunable parameters here. And Usman, let me know if I missed anything. So the first one, I think I've already mentioned, that's the batch size. So these worker processes that are reading from streams will read that batch size of events, run the continuous aggregation on it, and then output that to the combiner process. So that's the first parameter that's relevant here. If you have a smaller batch size, you're going to be executing these worker plans more frequently, and vice versa. And the second configuration parameter is how often the combiner process will commit to disk. So you can tell the combiner process to keep taking these batches from the worker and continue aggregating them in memory, and then every so often commit that to disk. And that defaults to something, I think, 50 milliseconds, which is pretty often, obviously. And then a lot of larger users will widen that commit interval to something on the order of seconds, so that the combiner just keeps aggregating in memory for as long as possible, and then only commits the result to disk every second or so.
And with the extent of the capabilities that Pipeline offers, I'm sure that there are some either niche features or some very high-level features that people might not necessarily go to immediately. So I'm curious if there are any of those that you have found to be particularly useful that are often overlooked initially.
Yeah, I would say what immediately comes to mind is some of the more advanced aggregates that we provide that use fairly interesting probabilistic data structures like Bloom filters and filtered space saving and things like that. And in the previous versions of PipelineDB, before we hit 1.0, they were kind of named after the actual data structures that powered them. So filtered space saving, for example, is used to compute top K, like heavy hitters. That's something where you want to say, what are my top traffic sources? Just keep the top 10 in memory or something like that. But it would be called, that one was called like FSS Ag, for example. And I think a lot of people, they weren't particularly familiar with what these data structures were and how they could be used to actually be helpful to them. And so I think we probably alienated some users by not giving those things more intuitive names. And so we actually renamed them in the recent 1.0 release. We renamed the aggregates and functions that use these data structures based on what they're actually for. So FSS Ag is now called Top K Ag. And then there's several others that follow the same examples. So I think a lot of people probably had no idea that these things could be extremely useful for them. So we're seeing more people use these aggregates now that they're named something more intuitive. I would say the other thing that is very powerful that users may not know about is the capability, and this really comes from Postgres, less than PipelineDB, the capability of implementing user-defined functions to include in your continuous views and transforms that can do whatever you want, basically. If there's something that if there's some computation that you need to run on your streams that you can't accomplish with the out-of-the-box functionality that PipelineDB gives you, you can fairly easily just write functions in any programming language you want and then start using those in your continuous queries. And it's actually super easy. I think a lot of people probably are intimidated by that, even though it's actually really easy to do with Postgres. Postgres has done a fantastic job of making that interface really usable for people. But I think a lot of users, they don't really consider taking that approach. So, Usman, did I miss anything there?
Yeah, I think one more thing which is like a pretty cool abstraction, and usually like if you try to do it with any other system, it's actually a very like complex problem to do, is the ability to form like kind of DAGs or like nested computations. So Derek briefly mentioned that there's two different types of primitives that PipelineDB offers. One is a continuous transform, which doesn't really persist anything to disk. It's kind of just like this thing where a stream comes in and a stream comes out. And then there's a view where kind of stream comes in and it persists some state to the database. So you can think of it as like a sink. But there's another cool thing that these views also output, is called, like, I think we used to call it like an output stream or a delta stream. I'm not sure what the exact nomenclature now is, but the idea is that every single time something changes in a continuous view. So for example, if you are doing something like, hey, I want to count the number of times this button is clicked every minute, every single time that count changes, say it changed from 5 to 10, a new event will be emitted in the output stream of that view, which will say the count changed from 5 to 10. And then that output stream can further be consumed by more transforms and views. So you can kind of make this giant tree of computation. And I think that's something that, like, a lot of times people, when they're thinking about how to design their queries, they don't think about it in that form. They'll just kind of have like a flat topology where they'll just create like 10 different views, where you could potentially make it a little bit more efficient by creating maybe like 2 views and then have 2 views which are kind of nested underneath it, and then maybe a final view which actually reads the output of the views, something like that. So I think that's just a little bit more of like a complex way of thinking about things, but it does make the system a lot more efficient because you are reducing the amount of compute that you have to do.
Yeah, that's a really good point. I'm glad you raised delta streams. I'll just make a quick note on delta streams. These things are very cool. As Usman said, each change made to a continuous view is essentially emitted into a new stream. So you can think of the streams like, okay, +2, +1. We just had to change the count from 3 to 4, from 4 to 5. And you can consume that stream of changes to ultimately change the aggregation level of an upstream continuous view. This is a very, very common pattern with PipelineDB that people do. So a lot of users will say, okay, start aggregating into 1 minute buckets. So for each minute, I have a row with all the aggregate data, but then that table could get pretty big, obviously, over the course of weeks or months. So they'll say, okay, set the time to live on that upstream continuous view to a week. Any data older than a week will be automatically purged in the background, and then you could consume its delta stream to aggregate that data into a lower aggregation level, like day or month, for example, which would allow you to keep it for a longer term without basically the same information over a longer term, without letting the initial upstream continuous view grow without bound.
And that seems like it would be very useful for people who are leveraging Pipeline for a systems monitoring type of use case. And it also brings some possibilities in terms of alerting capability, where you're using the continuous view to keep the current value updated, but then you can also use the delta stream. For instance, if you're computing it every minute, compute another continuous aggregate over the delta stream for the past 10 minutes or something, so that you can do something like a standard deviation, where if one of the values in that delta stream is outside of a normal bound, use that to trigger some function which might generate an alert.
Right. Yeah, exactly. So I would say that probably 75 or 80% of the PipelineDB use cases are in the areas that I mentioned before, powering real-time analytics dashboards, things like that. And then the remaining portion of the use cases are pretty much exactly what you just outlined, doing things like real-time alerting and monitoring, and things like that. So yeah, that's absolutely something that users do.
And in terms of consuming the output of the continuous views in real time, I'm wondering if there are any built-in functions of PipelineDB for being able to push that information to the consumers, or if it's something where you would just pull that table on whatever time interval you care to view the output.
Yeah, so in general, the approach would be let's think about a dashboard, for example. The user sets a date range, and then that would issue a query to PipelineDB, and then the result would just be rendered. So it's more on demand. I wouldn't necessarily say that people like continuously pull PipelineDB. It's more so that whenever they want to know the most up-to-date result, they'll just issue a query to the system, whether that's a dashboard or a person or whatever, because all of the aggregate data is just always up to date. So every time you query it, you'll get the most up-to-date result, and it's usually very fast and low latency because you're not scanning and aggregating all of this granular data over and over and over again on demand. So that's the primary way that people get data out of the system. And then there are ways to push data out to consumers also. This kind of goes back to the user-defined functions topic that I briefly talked about. People have written their own functions that push data out to a Redis pub sub channel, for example, that some other application is connected to subscribe to the most recent results and things like that. And then, for example, our Kafka connector that people use to natively connect PipelineDB to Kafka. It's primarily used for consuming data from Kafka into a PipelineDB stream. It also has the capability to push data back into Kafka, though. So you could achieve an alert by monitoring the output of a continuous view in the way that you just described, and then when the value hits some certain threshold, push an event out to Kafka, which would be consumed by some other client somewhere.
And in the process of building and maintaining and growing the PipelineDB project and business, I'm wondering what you have found to be some of the most challenging aspects and some of the most interesting or unexpected lessons learned in the process.
I mean, I think building this kind of infrastructure is inherently very, very challenging, which makes hiring extremely challenging as well. So that's a huge challenge. And then specifically in terms of the type of thing that PipelineDB is, this continuous processing system, that's an extremely difficult problem to solve because the system is always running and it can't fail. So anytime there have been like bugs or issues in the past with a big user, it becomes immediately clear because it kind of cascades across the whole system because it's just constantly running. Every millisecond of every second of every minute of every hour of every day, PipelineDB is running as fast as possible. And so it has to work really well and it has to be really efficient because of that, because it's not like more traditional systems that solve this problem and that they're only really doing complex work when someone issues a query to it. So it's just constantly perpetually running, and that's a really, really hard problem to solve. And in terms of the surprising ways that people have used our technology, I think a lot of the usage has been pretty much exactly what we thought it would be, because we're solving a pretty generic problem in terms of aggregating data. That's just a widespread, ubiquitous problem across all organizations. So a lot of it, I would say, hasn't been particularly surprising, but there are use cases here and there that do surprise us. I would say like one in recent memory is an embedded use case. So companies have some sort of product that they may deploy geographically, like a CDN, for example, and they want to do some computation or aggregation on data being produced at the edges so that they don't have to send a bunch of granular data back to some central repository. And we're definitely starting to see use cases like that, which are actually fairly surprising, I would say. Is there anything else I missed, Usman?
I think one of the things, maybe at least like in the beginning, I think PipelineDB was like when we started building it, we didn't focus that much on the time series aspect of things. It kind of was like this, like an overall generic stream aggregator. But I think over time it seemed like, which I guess kind of makes sense, is that like a lot of the streaming data just ends up being time series data because it's some sort of event stream, and so it does have a timestamp associated with it. So a lot of the kind of like future work that happened in PipelineDB, like time to live, which says that, hey, after a certain point, just drop the data that's older than this time, or like sliding window queries. Like I think a lot of work went into that, whereas maybe we hadn't like focused on it from the very get go. But like in retrospect, it seems pretty obvious that that is what we should have expected.
Yeah, that's actually a really good point. I'm glad you brought that part up. So I would say overall, PipelineDB is not, at this point, I wouldn't call it like a stream processing engine or a streaming analytics engine or anything like that. It's absolutely a time series analytics engine. And the reason is that when you talk about things like stream processing, there's a particular capability in that discipline that I would call, event by event ordered processing, where users want to say, if this event happens, then this one, and then this one, do this. And most traditional stream processing systems will have that capability as a first class feature. We never added anything to facilitate ordered event by event processing. We never wanted to. And so when you look at like a stream processing engine minus event by event ordered processing, what you end up with is time series analytics. So that's definitely what PipelineDB has come to be, not a stream processing engine, but a time series aggregation engine.
Yeah, and that brings up one other question too, in terms of the challenges of being able to process those unbounded time-oriented streams of data, is some things along the lines of processing out of order events and figuring that out. But that's definitely something that's more in terms of the specific use cases of the user.
Right. Yeah. There are, what we found with PipelineDB, there aren't many requirements to perform any sort of ordered event by event processing. Usually, if people have that requirement, we'll tell them that PipelineDB probably isn't the tool that they're looking for. Because if you're doing a lot of aggregation, you almost by definition don't care about ordered event processing. So given that all of our users and customers use PipelineDB for very high throughput aggregation, there's never really a need for ordered event processing.
And you already answered the question a little bit, but are there any other cases where PipelineDB would be the wrong choice and you would actively discourage someone from using it for a given use case?
Yeah. As I said, definitely strongly ordered event by event stream processing. PipelineDB is not going to be the right system for the job in those cases. And then there are a couple more. I would say, obviously, if you're not using SQL, or if the continuous queries that you're running on this data can't be expressed within the abstractions given to you by SQL, then PipelineDB is definitely not going to be a fit because it's all SQL based. And I would say if you're doing a lot of ad hoc querying, PipelineDB is not going to be a fit either, because as I mentioned, all of these aggregation queries, you have to know them in advance, declare them in advance, and then the results just start updating from that point forward. So if you're running a lot of ad hoc queries, then a system like that it's going to be too restrictive for you. And so we would actively discourage people from using PipelineDB if they had a lot of ad hoc queries they wanted to run. And by a lot, I mean the vast majority of the queries running against the system would have to be ad hoc. There's like an analyst somewhere connected to the database, and every single query that she runs is different from the one before. Then PipelineDB would be a little bit too restrictive. I should also mention, though, that the output of continuous views, as we've discussed, is stored like just regular SQL tables. So you can further query those however you want. You can run further aggregation queries on the output of a continuous view. You can join the results with another table or continuous view. So people do a lot of further final processing on the continuously updating output of continuous views. But if you really need to run a lot of unique ad hoc queries, on all of your granular data, then PipelineDB is not going to be the right tool for the job.
Yeah, I think the other thing to mention here would be that even when you're doing stream aggregation, like it only makes sense if you're aggregating your data down by a lot. Like say if I have a stream where my typical aggregate row, it only processes on the order of like 1 or 2 events. And so at that point, like my aggregation there is basically not really reducing the input size that much. So if I have a billion events coming in and I end up storing 900 million rows, it's not really doing any like large aggregation. So PipelineDB is like shines the most when the input size versus the output size is like an order of magnitude or 2 orders of magnitude different. I think that's when PipelineDB is extremely efficient, and that's kind of like the crux use case for it.
Derek, your comment too reminded me of one of the other things that we didn't discuss earlier that we don't necessarily need to dig into, but that because of the fact that the aggregations are being computed within the boundaries of your Postgres database, it also enables you to join that information to existing tables so that you can enrich the events as they're coming in with additional facts and metadata that you already have stored from other tables and other applications potentially, which is one of the other ways that it stands out from a generic stream processing engine.
Right. Yeah. As you mentioned, because everything's happening basically on top of Postgres, you can include other relations like tables and views as part of a continuous views definition. So you can join a stream onto a table and then run your query on that joined result. So the example you mentioned is spot on. What a lot of people will do is their events coming in may have like a user ID, for example, like a number, but they want to run queries on more than just the user ID. They might want to attach the user name, the user account number, or the user's geographical location, whatever the case may be, and they can use stream table joins to achieve that.
And so now that you've hit the 1.0 milestone, I'm curious what you have planned for the future of PipelineDB.
Yeah, we've been really excited to get the 1.0 release out. It's been less than 2 months since we released it, and it's 1.0 is already the most popular version that of PipelineDB that people are running, which is crazy because the other releases have been running for multiple years now. So I think packaging it up as an extension really just made things a lot easier for people. And in terms of looking forward, the next major piece of functionality that we're excited about adding to PipelineDB is partitioning automation. And what that means is currently continuous view tables are stored as just a single table. And so if those get really, really big, the query performance in terms of retrieving data from it and querying data can degrade over time as the continuous view continues to grow and grow and grow. And for ones that are really big, that can be problematic. Nobody wants to see their query latency slowly increase over time. So what partitioning automation is going to do is that continuous views will be structured as multiple separate tables. They'll behave as one logical table still, but they'll be physically stored on disk as many separate partitions of the same data. And what this does is it bounds the query performance by basically whatever the partition size is. The query latency will never get worse than it is for a full partition. So what users are going to be able to do is say, make the partition width 1 day, for example, and then as data's in the continuous view is filling up, as soon as the current partition has 1 full day of data, then a new partition will be automatically created and that one will be populated moving forward. And when you query them, they'll be combined implicitly by the query engine. So as I mentioned, it still behaves as one giant table, but they'll be physically partitioned on disk, which will be a huge performance win. And then the other thing I'll mention is integration with something like TimescaleDB. That's definitely in the works, and a lot of people have been asking for that. So I think we'll be really happy to get something out in that area moving forward as well.
Are there any other aspects of PipelineDB or the work that you're doing at the business aspects of it or anything along those lines that we didn't discuss yet, which you think we should cover before we close out the show?
I think things have been pretty well covered. Usman, can you think of anything?
Well, for anyone who wants to get in touch with the both of you, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get each of your perspectives on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I can start off on that, I guess. Yeah, so I think for me, and that's I think one of the things about PipelineDB that I thought always was super exciting was that in general, when we think about data management or data processing or tools like that, the thing that's typically discussed is the performance. Everyone's excited about the performance. Hey, how fast is it? How many rows does it do per second? How much can it store? Does it scale this, that? And the thing that's almost never mentioned is what is the usability of this tool? How easy it is for me to install? How easy is it for me to actually write a query? A lot of times I'll see that even to deploy a new query, you have to write some code, write some Java, write some Scala, actually deploy it to a server, do a release, ends up taking half a day. And I think that's kind of the biggest thing for me. And I think we've seen some trend as of recently with things like, I don't know, CockroachDB or PipelineDB and a few other new databases coming out, which have focused more, or I think there was RethinkDB was one of them also, who have focused more not just on the performance, but also on the usability aspect of things, that let's not just make it fast or something which has a lot of features, but let's also make sure that it truly makes the lives of developers easy. They don't have to spend a lot of time deploying it. They don't have to spend a lot of time actually adding more functionality to it or adding a more new query to it or adding a new node to it. Let's just try to make it as kind of self-serving as possible. And I think that's we've seen a recent trend towards it, which is pretty good. But I think traditionally that's probably the thing that's been the most annoying about this entire space, is that it's just very difficult for anyone to get started.
Yeah, I would say I can't think of anything I would say beyond that. I think I would agree that that's probably the biggest, most widespread gap in tools in this space, because otherwise, honestly, I think the state of the technology available in the space of data management, my honest take is that it's actually really good. There's been a lot of innovation over the years, particularly in recent years, and you can pretty much at this point find a tool for processing and managing data that's actually pretty good. Most of them are highly specialized because they're all, generally all these different systems are focused on doing one thing relatively well. And that's generally because in order to get scalability and performance, you typically have to sacrifice flexibility. And so the result of that idea is that there are a lot of tons and tons and tons of very specialized tools out there. But honestly, I think that the state of the art in this space has never been better, and there's something pretty good out there. Probably many tools that are pretty good out there for pretty much anything you want to do. And yeah, as Usman mentioned, usability is the only real widespread deficiency that I would say exists.
Well, thank you both for taking the time today to join me and discuss the work that you've done with PipelineDB. It's definitely a very interesting project and one that fills a very useful space, particularly for people processing large volumes of data. So I appreciate you taking the time, and I appreciate your efforts on the project, and I hope you enjoy the rest of your days.
Thanks for having us.
Likewise, thanks for having us, Tobias.